Want to understand Einstein and his theory? Without mathematics, and especially without non-Euclidean geometry, it's not possible. Why? Because the space-time we live in, the one with 4 dimensions, is curved, and that's why it's described by a non-Euclidean geometry. Maestro, cue the tape. The space-time we live in has 4 dimensions, 3 of space and 1 of time. In addition, it is also curved. How can we visualize this? Without an analogy, it's almost impossible. In the book Physica Povestita, I used the analogy of curved 2-dimensional surfaces. They have only 2 spatial dimensions. To begin with, let's say that Euclidean geometry applies to flat surfaces, such as, joking a bit, the surface of flat Earth models. We can also consider the surface of a curved object like an unbent corner of printed paper. According to Euclid, these are surfaces on which, through a point, only one parallel can be drawn to a given straight line. That's where the name Euclidean surfaces comes from. The distance between 2 points is calculated from the coordinates of the points using the Pythagorean theorem, and the sum of the angles of a triangle is 180 degrees. That's what we learned in geometry. On the other hand, non-Euclidean geometry is for curved surfaces, for example, a sphere. Here, the distance between 2 points measured on the surface, pay attention, will need a different formula than the Pythagorean theorem. As we will see, through a point there can actually be more than one parallel to a given line, and the sum of the angles will be different from 180 degrees. For example, the spherical surface of the Earth. Here we define a straight line, as in the Euclidean case, as the set of intermediate points that make up the shortest distance between the two on a surface. Note that in technical terms it's called a geodesic. Here's an example on the spherical surface of the Earth. Do you remember, the meridians are those lines that cross the Earth from north to south. If we choose 2 cities located on the same meridian, one to the south and the other further north, the line that defines the shortest distance between the 2 cities is actually the meridian. The meridian is then a particular geodesic. Note that any geodesic on a sphere is a curved line, a circle that divides the Earth into 2 equal hemispheres like the equator. Parallels are not geodesics. Now let's test Euclid's principle on the curved surface of the Earth, taking a point on the equator, the meridian passing through it, which is a geodesic, and a neighboring point. If we draw a geodesic through the neighboring point, the equivalent of a straight line on Euclidean surfaces, so that the geodesic is as parallel as possible to the first meridian, it will eventually meet another geodesic, which is also a meridian. The problem? The 2 meridians meet at the North Pole and the South Pole. So we have a non-Euclidean geometry because the straight lines of geometry, the geodesics, always meet, in this case at the poles. There are no parallel geodesics like there were parallel straight lines on flat surfaces, but that's not all. Look at this triangle ABC on the surface of the sphere. It is made up of 3 straight lines, that is geodesics, 2 meridians and an equator. You see how on the surface of the sphere, all the angles of this triangle are right angles. Now the sum of the angles becomes 270 degrees. This is another feature of Euclidean geometry, because the value is different from 180 degrees. Mathematicians have shown that there are basically 2 types of curved surfaces, elliptic and hyperbolic. On elliptic curved surfaces, 2 parallel geodesic lines meet, and the sphere is such an example. On hyperbolic surfaces, through a point, we can draw several parallels to a given straight line, which never meet again. An example of a hyperbolic surface is a horse saddle, or the saddle that forms on the ridge of a mountain. As we all know, when making a flat map of the Earth, it does not accurately reflect the distances between cities and areas, which is surprising. The cities on the spherical Earth are now transposed onto a flat surface of paper. Another example is this. Here you can see how on the map the shortest distance between 2 cities, the geodesic, is not a straight line, something we realize by following airplane flights. Thus, to fly from Bucharest to New York, a plane will choose a trajectory similar to the one in the figure. Also, two equal distances on the map may not be equal in reality. For example, points C and D are actually closer to each other than A and B because they are located closer to the South Pole. So, how do navigators orient themselves on the flat map of the Earth when the areas on the map do not reflect the real distances? Essentially, they distinguish between the coordinates of points on the map, which can be any numbers, and the real distance between points, which is no longer simply the difference between coordinates as we were used to. And to be defined, it also needs another mathematical quantity called a metric. Look at this arbitrary coordinate system on the curved surface. In the figure, an arbitrary coordinate system xy is shown on the surface of a sphere. The actual distance between points D21 and E12 is calculated using the metric elements denoted by gx, gxy, and gy, which are different at each point in space. But with similar values for neighboring points, the general procedure is as follows. To begin with, we draw a global coordinate system on the curved surface, which can be any system we want. We will describe it using the coordinates x and y. Next, specifically for this coordinate system, and only for it, we will need to identify a matrix of 4 real functions. Basically, at every point in space, we will have 4 real numbers, denoted here as gxx, gxy, gix, and gyy. That's why, throughout the entire space, we will actually have 4 functions, gxx, gxy, and so on. It's very important to mention that the choice of these 4 functions depends on the chosen coordinate system. Other coordinate systems, other functions, what are they useful for? Well, by using these 4 functions, we can finally calculate the distance between 2 points on a surface using this formula. Here, delta x and delta y are the differences between the coordinates of these 2 points, and d is the distance between the points. What values do the functions gxx, gxy, and gyy take depending on position? They are the metric functions g at one of the 2 points, or an average, because it doesn't vary much over small distances. We see here how only gxy appears. That's because gx is equal to gxy. The matrix G is symmetric. What is this formula? For someone who loves mathematics, it's easy to recognize. It's the generalized Pythagorean theorem. This can be seen in this drawing. In very small areas, the lines of the curved coordinate system form parallelepipeds. Moreover, in these small areas, we can consider the surface of the sphere to be flat. That's why we can apply the generalized Pythagorean theorem to find the distance between B and C using the distances delta x, delta y, and the angle alpha. To make it clearer, in the book Physics Told as a Story, I calculated the metric, the 4 g functions on the surface of the sphere within the spherical coordinate system. It's not hard, high school geometry is enough. Here on the left are the spherical coordinates, and on the right is the calculated g metric, which depends on the coordinates through the beta and phi angles. Up on the right is the distance between 2 points, calculated on the surface of the sphere. Notice that we managed to describe the spherical surface using only coordinates on its surface through the metric. This is crucial because in the future, we'll need to describe our 4-dimensional space using only coordinates within it, drawn from the space itself, and will succeed just as Einstein taught us. The approach above also shows the generalization Einstein sought. We can choose any coordinate system to describe the world with it, as long as we determine the associated metric g. When we change the coordinate system, we will also have to derive the new metric g for it using the metric's transformation laws. In such a way that the distances remain the same. In fact, in general relativity, we talk about a metric tensor, precisely because a tensor follows certain transformation rules. The book Physics Told as a Story is full of formulas. And that's because I didn't write it by reading other popular science books, but because everything I described there, I worked through mathematically. So, basically, I solved the equations myself. And let me give you an example. Here is the calculation of the metric of a sphere, which I worked out myself and which you can do as well. That's why I'm giving it to you as an example. You can see the image of a sphere here. We have 3 points, A, B, and P. What interests us is the distance between points A and B when A and B are very close to each other. Of course, that distance can also be calculated using Cartesian coordinates. But now we're interested in expressing that distance in coordinates on the surface of the sphere, So what are those coordinates on the surface of the sphere? Essentially, they are the two angles, the phi angle and the theta angle. So we want to express the distance between A and B only through those two angles, phi and theta, because the radius of the sphere is given. And we can do this starting from the Cartesian coordinates. This is shown in the formula. Here are the Cartesian coordinates. However, let's look at the figure. And we actually see that we have a small right triangle there, because triangle ABP is a right triangle when it is very small. And the legs of this triangle AP and PB can be determined. AP is, for example, r multiplied by d theta, and PB is r sin theta multiplied by d phi. We see this from the triangles that appear there, and that means we can write this relation, that d squared, meaning AB squared, from the Pythagorean theorem there, is r squared d theta squared, meaning AP squared plus PB squared, which is the second term. R squared sine squared theta d phi squared, yes. And this is essentially the metric of the surface. Why? Because I expressed the distance between two nearby points on it using the coordinates on the sphere, meaning theta and phi. And we just need to look at our formula, which is the general one with the metric where g appears. And in this case, it will be g theta theta and g phi phi. And let's make the connection to see which is which. And we immediately get the metric of the surface, which contains, of course, r, because r is the radius of the sphere, and it also contains theta. We see that it doesn't depend on phi. That is, we manage to express the geometry of the sphere only with the elements that are found on the sphere, namely theta and the coordinates on the sphere. That's pretty much the whole idea of non-Euclidean surfaces, to be able to describe them only with the elements that are on those surfaces. And with that, we've reached the end of the introduction to non-Euclidean geometry. Next time, we'll apply this to space-time. Until then, please subscribe if you haven't done so yet by clicking the subscribe button right now. I thank those who support us on Patreon and those who have become channel members here. I am Christian Prasura. You are cool. I wish you all the best. Goodbye.